Why don't more infant formula companies use organic, grass-fed whole milk instead of skim? Why don't more infant formula companies use the latest breast milk science? Why don't more infant formula companies run their own clinical trials? Why don't more infant formula companies use more of the proteins found in breast milk? Why don't more infant formula companies have their own factories instead of outsourcing their manufacturing? We wondered the same thing. So we made ByHeart, an infant formula company on a mission to get a lot closer to the most superfood on the planet, breast milk. Our patented protein blend has more of the important and most abundant proteins actually found in breast milk. We're the first and only US-made formula to use organic, grass-fed whole milk, not skim. We even conducted the largest clinical trial by a new infant formula company in a quarter century, with clinically proven benefits like easier digestion, less spit up, and softer poops versus a leading infant formula. And we make our own formula in the USA and our very own factories in Iowa, Oregon, and Pennsylvania. ByHeart, a better formula for formula. Learn more at byheart.com.
Good morning, evening, and good day. Welcome to another episode of Astronomy Daily, the podcast where we muck about with space, science, and stuff for your listening enjoyment. I'm Steve, your host. It's August 14, 2023.
Astronomy Daily, the podcast, with your host, Steve Dunkley.
Indeed. And in today's payload, we have a new technique that measures structured light in a single shot, a look at basic astronomy setups, travelling without moving, and plans for regular moon shuttles. The works. So stay with us on Astronomy Daily. And would you welcome our co-host, Hallie?
Hello, everyone. Glad to be down under again. It was nice to hang out with Tim last week in England. You know I love traveling even if it is at the speed of light.
Well, it's funny you should mention travelling. We've got that story about travelling today.
The one about how far we all move.
Well, I like to call it travelling without moving, Hallie.
Another sci-fi reference there, I see.
Yes, so there's that one, and we'll be talking about the many plans for getting all the infrastructure to the moon. So many different projects and industries and countries are working on lots of stuff to get there.
They all want to get to the lunar surface. There's talk of a colony, mines, and regular shuttles, Steve.
Yes, that's the way it looks. Looks like Artemis is just the beginning, so we'll have a look at that later on. And you have a really confusing story about light.
I do. It's about a new technique to measure structured light.
Okay, structured light?
It's really exciting stuff.
Well, okay, I believe you, Hallie. I'd better let you get to it. I know your legion of super brainy listeners are hungry for that one. I'll admit that I read the story earlier and it was a bit scary, mostly.
Enough with the sci-fi references already.
Fair enough. Okay, Hallie, let's have those short takes.
Hold on to your thinking caps. Structured light waves with spiral phase fronts carry orbital angular momentum, OAM, attributed to the rotational motion of photons. Recently, scientists have been using light waves with OAM, and these special helical light beams have become very important in various advanced technologies like communication, imaging, and quantum information processing. In these technologies, it's crucial to know the exact structure of these special light beams. However, this has proven to be quite tricky. Interferometry, superimposing a light field with a known reference field to extract information from the interference, can retrieve OAM spectrum information using a camera. As the camera only records the intensity of the interference, the measurement technique encounters additional crosstalk known as signal-signal beat interference (SSBI), which complicates the retrieval process. It's like hearing multiple overlapping sounds, making it difficult to distinguish the original notes. In a recent breakthrough reported in Advanced Photonics, researchers from Sun Yat-sen University and École Polytechnique Fédérale de Lausanne used a powerful mathematical tool called the Kramer's chronic relation, which helps with understanding and solving the problem. This tool enabled them to untangle the complex helical light pattern from the camera's intensity-only measurements for single-shot retrieval in simple on-axis interferometry. Exploring the duality between the time-frequency and azimuth OAM domains, they apply the Kramer's chronic approach to investigate various OAM fields, including Talbot self-imaged petals and fractional OAM modes. The new measurement technique has great potential for advancing technologies that rely on these special light patterns. According to corresponding author Jianqi Hu, now a postdoc at Laboratoire Kastler Brassel, École Normale Supérieure, France, the proposed method can also be generalized for OAM beams with complex radial structures, making it a powerful technique for real-time measurement of structured light fields, simply by a snapshot with a camera. Compared to conventional on-axis interferometry, the Kramer's Kronig method demonstrated by the researchers not only accelerates the measurement but also makes it much simpler and cost-effective. Thanks to this new technique, scientists have gained a powerful means to unlock the secrets of structured light waves with OAM. This breakthrough has the potential to revolutionize various technologies, paving the way for exciting advancements in the field of structured light in the near future. Seeing Saturn's rings through a telescope can be an awe-inspiring experience. Now is a great time to check them out. Many amateur astronomers use a backyard telescope to see Saturn, and seeing the ringed planet through a telescope eyepiece is one of the most exciting moments for any amateur skywatcher. Many enthusiasts state that seeing Saturn through a telescope was the reason they became fascinated in space for life. Keep in mind that you probably won't see a NASA-quality image of Saturn using a backyard telescope, but so many have been surprised at how satisfying a real-time view of this planet is. It's definitely worth a try. Many beginners start out with a simple 4.5 Dobsonian telescope, which features a large aperture for its price range and is a good starter telescope. This affordable telescope has enough power and magnification to see Saturn's rings in all their glory. Planets like Saturn and Jupiter are usually easy to spot. They look like bright stars. Check for their location with an app and then use your telescope to reveal their true identity. Generally speaking, the size of the planet in your field of view will depend on the equipment you are using. But this comes with experience and know-how. With some practice and experience, you'll be visualizing great live moments with the giants of our solar system. Boeing Starliner Crewed Flight Test, CFT, which will carry astronauts Barry Butch Wilmore and Sunita Suni Williams to the International Space Station (ISS), is now delayed to next year, with the earliest chance for launch in March. However, Boeing is still confident it will complete the 6 crewed flights ordered by NASA despite the planned demise of the ISS in 2030. NASA and Boeing shared the updated launch information in a press briefing on Monday, August 7. The Crew Space Transportation 100 CST-100 Starliner was supposed to launch its first crewed flight on July 21, but Boeing found several issues that could have posed a threat to the safety of the astronauts, such as flammable tape and weak parachute soft links, causing yet another mission delay. Boeing CST-100 Starliner, along with SpaceX's Crew Dragon, is part of NASA's Commercial Crew Transportation Capability (CCT-CAP), which aims to have 2 vehicles carry American astronauts and cargo to the ISS on rotation throughout the year, with the goal of ending the nation's sole reliance on Russia, according to the space agency. The companies were selected in 2014 for the contract, and while SpaceX has almost completed 7 crewed trips to the station, Boeing Starliner has been plagued with delays spanning years. And that's the short takes for today.
You're listening to Astronomy Daily, the podcast with Steve Dunkley.
Yes, it's good to see that Boeing is being very careful with their crew. I would not take that away from them. I mean, in recent years we've seen lots of delays with crewed flights and so on. But I really hope that Boeing can pull out all the stops and get Starliner operational to the point where we see more activity. This is just another step forward in getting all of those plans together for those grandiose plans of getting a colony and mining operations on the moon. I mean, who knows if that's a good thing or a bad thing? We'll just see how it goes. I mean, human history has shown that wherever we see opportunity, that's where we invest our activity. So let's just see how it all unfolds. Now, do you remember the comment in Dune by Frank Herbert, where the guild navigators would fold space and they would do this thing where they call travelling without moving? Now, whether you're a frequent jet setter or a couch potato like me, you you'd travel much more than you would imagine. In fact, you'd probably be even true if you were to stay perfectly motionless your entire life. How far, on average, does a person travel in their lifetime? The answer depends on whether or not you consider Earth an actual vehicle. As for the distance on Earth's surface, a typical human would travel 30,000 to 50,000 miles or up to 80,000 kilometres in their lifetime, though some globetrotters like my fabled brother Andrew from Space Nuts would probably go much further than that. Consider most people accumulate the majority of this mileage from commutes and quick errands. That's an impressively large distance. Enough to circumnavigate the globe at least once, but large as it is, the number pales in comparison to the motion we get by simply hitching a ride on our planet. It spins on its axis, and because Earth is mostly solid, it rotates on a single rigid body, essentially, meaning that everywhere on the planet experiences the same angular speed and everyone travels a full circle every 24 hours. But if you were to stand on the north or south geographic poles, you probably wouldn't actually travel anywhere. You just rotate or spin around and around. On those on the equator, however, would get tremendous amount of linear speed thanks to this rotation, roughly 1,000 miles per hour or 1,600 kilometres per hour. Most people don't live on the equator, however, so we can say that the average human is constantly travelling at roughly 930 miles per hour or 1,500 kilometres per hour. As we see, precision doesn't really matter in this equation, but when you add up over roughly an 80-year lifespan, each person travels around 600 million miles or 1 billion kilometres in a lifetime. That's a tremendous leap above the travel we do on Earth's surface, but we're just getting warmed up. In addition to rotating, the Earth orbits the Sun. That orbit is an ellipse, which causes our planet to occasionally move more quickly or slowly, depending on its distance from the Sun. But on average, Earth's orbital speed is about 19 miles per second, or 30 kilometres per second. That's about 600 million miles, 1 billion kilometres every year. So over a lifetime, each of us travels roughly 15 billion miles or 80 billion kilometres, which again dwarfs the distance we travel due slowly to our rotation of our planet. But Earth is not the only object in motion in the universe. The Sun travels in a long, lazy orbit around the centre of the Milky Way galaxy. Of these galactic years, it takes roughly 230 million Earth years to complete. To put that into perspective, life first rose on Earth, so they say, around 17 galactic years ago, and in only 25 more galactic years the Sun will die. So the story goes. Compared with these enormous galactic scales, a human lifetime is barely perceptible and the Sun barely inching along its orbit, but on a human scale it's almost incomprehensible. Due to the motion of the Sun orbiting the centre of the Milky Way, each of us will travel around 370 million miles, 600 billion kilometres, in a lifetime. And it doesn't stop there. Our entire galaxy is in motion too. All galaxies are, on average, flying away from each other, but that's due to the expansion of the universe. On top of that expansion, each galaxy has some motion of its own, something astronomers dub peculiar velocity. You might have noticed this in some nightclubs, perhaps. For example, the Milky Way is on a collision course with our nearest neighbour, the Andromeda galaxy. The mutual gravitation attraction is enough to overwhelm the general expansion of the universe, and in about 5 billion years, so the story goes, these galaxies will begin to merge. On top of that, both the Milky Way and the Andromeda are headed toward the Virgo cluster, a massive cluster of galaxies about 65 million light years away. Beyond that, the Virgo cluster and its surrounding galaxies are all headed toward the Great Attractor, which is the centre of our supercluster called Laniakea. Astronomers can calculate the combined motion of these gravitational influences by observing the cosmic microwave background, which is composed of radiation released when our universe cooled from plasma state when it was only 380,000 years old. It completely soaks the universe and is the same to 1 part in a million across the entire sky. Any motion in the universe will be visible in the CMB. Light in the direction we're headed will get Doppler shifted to higher frequencies, blue shift, and light in the direction we're moving away from will be shifted to lower frequencies, red shift. By measuring this shift, astronomers can calculate our total velocity through the universe, and those measurements give a number of around 390 miles per second, that's 630 kilometres per second. When you add up that over an 80-year lifespan, it gives you a total movement of 930 billion miles, or 1.5 trillion kilometres. Even if you never leave home, you will still travel that enormous distance, and that's quite an accomplishment. Now, I mentioned earlier on a little bit about the plans to send shuttles to the moon. Now, multiple space agencies plan to send astronauts, cosmonauts and taikonauts to the moon in coming years in a long-term goal of establishing permanent human residence there. This includes NASA-led Artemis program, which aims to create a sustained program of lunar exploration and development by the decade's end. There's also a competing Russian-Chinese International Lunar Research Station effort to create a series of facilities on the surface and or in orbit of the moon that will enable lucrative research. Beyond these government-led programs, there are many companies and non-government organisations hoping to conduct regular trips to the moon, either for the sake of lunar tourism, and mining to build International Moon Village that would act as a spiritual, for the want of a better term, successor to the International Space Station. These plans will require a lot of cargo and freight moving between Earth and the moon well into the next decade, which is no easy task, as you can imagine. To address this, a team of US-UK researchers recently released a research paper on the subject to optimise trajectories for travelling between the Earth and the Moon. The team consisted of Professor Emeritus Thomas Carter from the Eastern Connecticut State University and Mathematical Sciences Professor Mayahumi from the Worcester Polytechnic Institute. For the sake of their study, the preprint of which is available online, Carter and Humi explained how a shuttle could transport supplies to a lunar outpost and carry back resources extracted from the surface. Now, based on their calculations, they concluded that a trajectory that places the shuttle into an elliptical orbit and minimises the thrust requirements would be optimal. During the space race, both NASA and the Soviet space program relied on free return trajectories to send missions to the moon. This consisted of using the moon's gravitational pull to perform a figure 8 shaped manoeuvre, resulting in the spacecraft returning home with only minimal orbit adjustments, minimising the amount of propellant needed. The orbits of Artemis missions will be similar to the Apollo predecessors in that they will also perform the figure 8 flights that end with a splashdown in the ocean. In other words, these missions will be one-way trips, but beyond returning astronauts to the moon, assembling the Lunar Gateway and establishing the Artemis base camp on the surface, the long-term aim is to use the Artemis infrastructure to create a permanent human presence on the moon. There's also the need to keep things cost-effective, of course, which makes launching heavy payloads from the surface to the moon inefficient. Professor Humi explained one of the functions is to avoid sending large loads to low Earth orbits. Instead, we use capsules with provisions and replacements for astronauts to accomplish lunar settlements with minimum cost. We need something similar to the ISS, but with an orbit around the Earth and the Moon. This shuttle will never land on Earth or the Moon. Capsules from Earth will dock with it and when it is close to Earth, and similarly, capsules from the Moon will dock with it when it is near the Moon. This will avoid the need to lift large loads from Earth or the Moon, and this will save a lot of money and resources. However, the shuttles will need engines and propellant to keep this shuttle in orbit, as it will is subject to gravitational perturbations from the Earth, the Moon and the Sun. While the shuttle will not require the massive thrusters and propellant tanks needed to break free of Earth's gravity, engines and propellant add significant amounts of mass to a mission, which drives up costs. To address this, Humi and Carter considered manoeuvres that would minimise fuel consumption and allowing the shuttle to circle the Earth-Moon system in a reasonable amount of time. The process we used to obtain our results was to develop proper mathematical models based on gravitational forces of Earth, the Moon and the Sun that impact the orbit of the shuttle, said Humi. From this, they determined that a circular elliptical orbit with a perigee near the Earth and an apogee beyond the Moon would be an optimal trajectory. Only minimal thrust would be required for course corrections. This type of shuttle and trajectory, said Hermy, is needed for any plans to establish a permanent human presence on the Moon, but could also lead to a thriving Earth-Moon economy.
That was a real mixed bag today.
Oh, it sure was, Hallie, and we'll do it all again next week, won't we, Hallie?
Absolutely. Now where can they find us?
Well, you can go to Space Nuts Podcast Group on Facebook, and that's a great place for interactions. Love to see you all there. And you can listen to all the back editions of our parent podcast, Space Nuts, with Andrew Dunkley and Professor Fred Watson, and all the back editions of Astronomy Daily with myself, Tim Gibbs, and Hallie, of course, at spacenuts.io and bytes.com. So that's where you go for all your back editions of all our podcasts. And that's it from us for another week. We'd love to see you next week here on Astronomy Daily. Bye for now.
Astronomy Daily, the podcast, with your host, Steve Dunkley.